pleasure and honor to announce our plenary lecture for today and plenary speaker. And it's the Clay lecture. So I would like to acknowledge here the funding of the Clay Institute for this first lecture. And the speaker for today is, it's a big name, and I'm a bit nervous actually. It's Cheryl Praeger from Australia. I think we all know her name very well. She's a professor emeritus now, and she has been 40 years with the University of Western Australia and done a lot of important work and won big prizes. And the main motive, I would say, on the work is the interrelation of combinatorics with group theory, which leads to of course, to the concept of group actions and then applications in combinatorics, like in algebraic graph theory, combinatorial designs, and others. And I would say this is also the theme of her talk today. The title is Codes and Designs in Johnson Graphs. And yeah, we all look forward to your talk. And so, Cheryl, please go ahead.
Thank you very much, Michael. Now I'm very pleased to be here. Of course, I wish I was in Durham, as we all do, but this is about as good as we could possibly imagine. I'm going to try to share my screen. And then to make it big. Is that working for most people? Terrific, thank you. Yes, thank you, Michael. Codes and designs in Johnson graphs with high symmetry. Well, because we're not in Durham, I'm actually in Perth. And so I want to acknowledge that my university's lands and the lands that I'm on are on the traditional lands of the Whadjuk people of the Noongar Nation, and I pay my respects to their elders past, present, and emerging. So the talk today will be going inside of Johnson graphs. We'll be looking at designs and codes, and it will be guided everywhere by symmetry. The sorts of codes we're going to look at are called SIT, strongly incidence transitive codes, and there'll be Delancre designs. I'll give examples and links, and there'll be plenty of open questions. A lot of the work that I will be talking about started off as joint work with my colleague Bob Liebler, and unfortunately Bob died in 2009, a few years before I was able to finish off our first major paper in the area. There's also some joint work with Max Neunhofer that I'll tell you about, and more recently, joint work with John Bamberg and Alice de Villiers, my colleagues at the University of Western Australia, and our PhD student, Mark Iopolo. Mark has just finished in the last year or so. So first, let's make sure that we all know what I mean by a Johnson graph. So a Johnson graph has got two parameters, V and K. It's based on a V element subset, capital V, and the vertices are all the K sets, the K element subsets of V. Here is a picture of the small one. And when I've got these labels on the vertices, I really think of them as unordered sets. So the vertices are K subsets, and the edges are all the vertex pairs, alpha, beta, K sets, which intersect in as big as it can be for distinct vertices, K-1 points of V. And this is quite nice in the Johnson graph because the size of the intersection tells you about the distance between any two vertices. So if the shortest path between vertices alpha and beta has length I, then that happens exactly when the K sets alpha and beta intersect in exactly K-I points. So that's the graphs. And from the way I've described them, you can see that the symmetric group of all permutations of V acts naturally on the K sets as automorphisms of the graph. And that's a pretty big subgroup of the automorphism group of the Johnson graph. There's also another map I'd like to explain to you. Let's call it tau. the map that complements every subset. So every subset of V gets mapped to its complement. And in particular, every K set gets mapped to its V minus K point complement. And this induces a graph isomorphism from JVK to JV V minus K. And because of this, we usually will assume that K is at most V over 2. Also, I could have defined the Johnson graph with K being 1, but in that case, the vertices would just be essentially the points of V, and I would be getting the complete graph. So I'm not really interested in that. So I'll assume that K is at least 2. And in fact, the full automorphism group of the Johnson graph is usually just the symmetric group of permutations of V acting on K sets. That's true if K is not equal to a half V, but if K is equal to V on 2, then this tau is actually an automorphism because V minus K equals K. And the full graph automorphism group is just the direct product of these permutations with the cyclic group of order 2 generated by tau. Mostly in this lecture, I'm going to work with sim V, even if K is V on 2. So we can just think of automorphisms as being permutations of the K sets. Okay, so I'm going to talk about codes and graphs. The reason that we're looking at codes in graphs goes back to 2 papers, one by Delsart, one by Biggs, as far as I know, independently, both published in 1973. And they suggest that we should interpret subsets of vertices, a subset, let's say C of vertices of any connected graph gamma as a code. And so you'll think of the vertices in C as code words, and you hope that they're sort of spread out a bit in the graph so that if you could imagine starting off at a code word V and moving to a vertex adjacent to V, joined to V by an edge, so a distance 1 from V, and you think of that as being introducing a single error into the code word. And it would be nice if the vertices were so spread out that you would still be pretty much closer to V than any other code word in the graph, in the code. So if I move from V to a distance 1 vertex U, and U is not in the code, it's not a code word, then I'm going to call U a neighbor of the code. So Delsart suggested that we should think of this partition, this distance partition determined by a code in a graph. So this is a picture of the vertex set of the graph. Here I've got all the code words, and next to it I'll put all of the vertices which are not code words but joined to some code word. So that's all the neighbors. And I continue in this fashion. C2 would be all the vertices which are distance 2 from some code word, but not a code word and not a neighbor, etc. So I will spread out, I'll get this distance partition. The last set will be, say, CR, R being the covering radius. Now, Delsart was interested in particular in the case where this distance partition is what we now call equitable. That means if I chose any one of these distance sets CI, and I chose a vertex in the graph in CI, then the number of vertices from V to vertices in CJ should depend only on I and J for any of the parts CJ. It should not depend on the choice of V in CI. Okay, it's pretty complicated. You won't have to remember this for very long. But if the distance partition is equitable, then Delsart called this graph, this code completely regular. And in his 1973 paper, Delsart explicitly asked about the existence of completely regular codes in Johnson graphs. So that's 1973. There was quite a bit of work done on this in the succeeding years. In particular, there were 4 pretty nice papers published variously from, say, 92 to 2003, 2 by Mayerovitz and 2 by Martin, Bill Martin. they found some completely regular codes. So here's a few examples in the blue box down here. You could take the code consisting of all the K sets containing some fixed small subset A of the set V. That's completely regular. Or you could take all the K sets contained in some fixed large subset A of V. These are all completely regular examples, but if you think about either of these two sorts of examples, you could imagine finding two code words which are sharing K-1 points of V so that they would have distance 1. And so the minimum distance in these examples is 1, the minimum distance between distinct code words. And unfortunately, over all these years, nobody found very many completely regular examples in Johnson graphs that had good error correcting properties. Because you can imagine if the minimum distance is at least 3 between code words, then I could introduce a single error, move distance 1 from a code word, and I would still be closest uniquely to that code word, so I could correct it. So there was very few with these, well, minimum distance at least 3. So this is when I started working with Bob Liebler. It was back in 2005. We decided to replace this rather global regularity condition of being a completely regular code with something much more local, but we wanted it to be pretty easy to check. And so we decided to make this local condition a symmetry condition. So we've got codes, and from now on, I'm going to just be talking inside of the Johnson graph. We've got a code in the Johnson graph. We're going to think of its automorphism group as the setwise stabilizer of the vertex subset C, the code, inside of SimV. And remember, symmetric group SimV is practically all of the automorphisms of the Johnson graph. So here is the automorphism group of the code. Of course, it's leaving C invariant, that's its definition. And so it's also going to leave the code neighbors set invariant. And so Bob and I decided to call the code neighbor transitive if the automorphism group is transitive both on C and also on the code neighbors C1. And this ensures that those regularity conditions are true if I think of vertices in C and in C1, but I'm not making any assumptions about any of the other parts of this distance partition. Now, one of the things we proved early on was that if we had a neighbor transitive code C in the Johnson graph, and if the automorphism group of C was not transitive in its natural action on the base set V, then the only neighbor transitive codes we get are actually these two families of completely regular codes. So they're completely regular and they're also neighbor transitive. But it means that we're going to be looking for some different sorts. And so we'll always have that the automorphism group is going to be transitive on the base set V. Now, another thing which kind of surprised us was that if we have the minimum distance at least 3 inside of a neighbor transitive code, then we get something more than we just defined. We get a special transitivity condition that I'm going to be referring to quite a lot. And so I've drawn a picture of it over here on the right-hand side of this slide. Now, this is a picture of the base set V. And so a code word gamma is a subset of size K of V. And then we've got the V minus K points in the complement over here. So I'm going to be looking at code words, gamma. I'm going to choose a point U inside the code word and a U prime outside the code word and look at those sorts of triples. Gamma's a code word, U's in gamma, U prime's not. And I want Aut C, or it turns out that Aut C is transitive on these triples. And so in particular, this means that it's transitive on code word, code neighbor adjacent pairs. And so they were sort of incidence transitive, but a bit stronger. So this property got called strongly incidence transitive, but let's just call it SIT. So we'll call a code with this SIT property an SIT code. Now, not every neighbour transitive code is SIT, but this is saying if you've got minimum distance at least 3, which is something we'd like, then it is SIT. Here's a tiny picture, or tiny example of one that you could go back and think about. It's a code of size 3 in that small Johnson graph I drew for you. It's neighbour transitive. It's got just 3 code words. Its automorphism group is this symmetric group of size 3. Oh, sorry, degree 3, size 6. And it's not transitive on these triples because there's actually 3 choices for gamma, 2 choices for u, 2 choices for u prime. That's 12 triples and it's just not big enough. So there are some neighbour transitive codes which are not SIT codes. Let's swap over now to designs and tell you the story there. I'll get back to codes in a bit. Okay, so we've got Johnson graphs. The vertices are k-sets. We might just as well interpret a subset of vertices as a set of blocks of a design and think of the pair V, the base set V, as being the points of the design, and the k-sets in my subset C being the blocks of the design. Now, if you use this point of view, then you're more interested in introducing different kind of regularity conditions than we did from the point of view of the code. So as a design, we might be thinking about T designs. So they will have the parameters V and K, which we've got already, and also a parameter lambda. And the condition is that every T element subset of points from V is contained in exactly lambda blocks from C. And if we're thinking about designs, then the sorts of combinatorial objects we're interested in would be flags of the design, which would be pairs, a block or a code word, a block gamma and a point in gamma, or they might be anti-flags, a block from the code and a point not in that block. And again, we're going to think of the automorphism group. Similarly as before, the automorphism group is going to be the setwise stabilizer of the block set inside of the symmetric group on V. So we've got these 2 interpretations of vertex subsets of Johnson graphs. They might be thought of as codes, they might be thought of as block sets of a design. And we might be asking, what are the links between the codes and the designs? And some of you that recognize this picture might be saying, why have you got a picture of Anne de Lancher? Well, way back, 1984, Anne published a very beautiful paper where she classified the anti-flag transitive, that is designs which are transitive anti-flags, anti-flag transitive to VK1 design. So the parameter lambda was 1. Every 2 points lies on exactly 1 block or line. Sometimes they're called linear spaces. And Anne noticed in her paper that, well, let me first explain down here in this box what she found. The examples were several infinite families of examples and 2 particular exceptionants. So there's projective spaces, there's affine spaces, there's Hermitian unitals, and there's these 2 exceptional examples. Now, she noticed that apart from these 2 exceptional non-Desarguesian affine planes, all of the other examples had automorphism groups, which were, and she expressed it, she stated this transitivity property. They all have the SIT property. And so we hadn't really noticed this until fairly recently, but we're going to call every design, whether it's a 2VK1 design or not, every design in a Johnson graph, we're going to call it a de Lancher design if it's got at least 2 blocks and it's got this SIT property. So we're going to look at de Lancher designs, and funnily, we've got the same property holding for designs as for codes. Okay, so we're interested, so to summarize, we've got this SIT property that we're interested in. If the subset has it, we think of it as an SIT code, and we also think of it as the block set of a Delancey design. And we note that for Delancey designs in particular, the automorphism group is transitive on flags, because we just forget about this third member of the triples here. And it's transitive on anti-flags if we forget about the second member in the triples. But it's a stronger property. So to be a Delancey design, you need a bit more than being transitive on flags and transitive on anti-flags. And of course, Anne noticed that this property was strictly stronger than flags and anti-flags because of her two exceptional examples. And we can find another exceptional example inside of this tiny Johnson graph that I've drawn here. If we take this code consisting of these 4 pairs, 1, 2, 2, 3, 3, 4, 4, 1, its automorphism group is dihedral of order 8. And there are too many of these triples for it to be a Delancey design, but it is transitive on flags and on anti-flags. Okay, so there's several examples like that. Let's continue. Where to next? Well, let me tell you a bit more about what Bob and I proved. So it was supposed that there's at least 2 code words, and that we've got our code being an SIT code, or think of it alternatively as a BC being a Delancey design. Then in this case, with the SIT property, ORTC has to be transitive on V. We don't pick up those horrible little completely regular examples at all. It's transitive. And so we might ask, does this automorphism group, I mean, being a group theorist, I would ask, does the automorphism group leave invariant a non-trivial partition of the point set or not? That is it primitive or is it imprimitive? Now, the thing that we could prove, which is kind of surprising, is that if the automorphism group is imprimitive, then you can get it by a particular blow-up construction that I'll tell you about in a minute of a smaller primitive SIT code. And if the automorphism group happens to be primitive on the base set V, then it happens to be 2 transitive. So there's something pretty amazing happening here. Yes. So let's continue. What about this blow-up condition? So let's suppose we've got an SIT code and the automorphism group is imprimitive on V. That means that there is, so this is a picture of V, there's a partition of V into equal-sized parts, and the elements of ORTC, the automorphisms, are just permuting around these parts, part-wise, set-wise. Now what happens here is that the size, the number of points is V, the number of parts, let's call it V naught, and all the parts have got the same size A, so we've got V is A times V naught. It turns out that the K in the Johnson graph is also divisible by A, so it's A times K naught. More than that, you can choose this partition, or, well, sorry, I'm getting ahead of myself. For any of these invariant partitions, there exists an SIT code C naught in this smaller Johnson graph with the V naught and the K naught parameters, such that the code words for C are precisely the unions of the parts of this partition which lie inside of the code words of C naught. So you just sort of blow up every code word of C naught and you get exactly the same number of code words, but they're just bigger, fatter. And you can always choose your invariant partition in such a way that the ORT C naught is primitive. So we can always construct our imprimitive SIT codes from primitive ones. So we're really interested in primitive ones. That's the code point of view. What about in terms of Delancre designs, if we've got an Aut C being imprimitive on V, what do I want to say about those before we continue? Well, in this case, the VC, the design, it is a Delancre design, but it can only be a one design. It is never a two design. But the smaller design, if we replace V by the partition U and C by the smaller code C0, that is always a two design, apart from a trivial case where the code words in C0 have just got size 1. So from both points of view, we're really, very interested in primitive SIT codes and very interested in point primitive Delancre designs. And remember what I said, if Aut C is primitive on V, then Bob and I proved that for an SIT code or for a Delancre design, that Aut C is two transitive on V. Two transitive means transitive on ordered pairs of distinct points. So the Delancre design's got no chance. If it's primitive, it's going to be a two design because it's got a two transitive automorphism group. Okay, so where to next? Well, the finite two transitive groups are known explicitly if we're willing to use the finite simple group classification. And it turns out that they give us lots of examples of SIT codes and lots of examples of Delancre designs. But one thing more, since we've got a two transitive group of automorphisms, if I were to take K to be 2 or V minus 2, then the automorphism group would be transitive on K sets and the code would be all the K sets. So they're a bit trivial. And so usually I'd assume that K is strictly between 2 and V minus 2, maybe at most V over 2. And think about what this has if we were looking at the giants. So perhaps some of us think immediately about two transitive groups as examples being the full symmetric group or alternating group. Here again, the only SIT codes are the trivial ones taking all K sets. As a code, the minimum distance is 1, not so interesting. As a design, the design is a complete design, so maybe not so interesting. So of course, we'll focus on the other two transitive groups. And we'll divide them up in a fairly rough division that I'm going to call sporadic. There's some which I'll call projective or rank 1 or affine or symplectic. Now, some of these we can deal with completely and get fabulous examples. Some we can't even complete. So I'm going to discuss these cases briefly, I hope, and it all fit in. So let's go. First of all, sporadic. What am I going to mean by sporadic two transitive groups? Please look at the blue box. Some of them come from sporadic simple groups. So there's all of the 5 Mathieu groups, MV, in their natural actions on V points with these values for V. And there's an exceptional action of M11 on 12 points. It's two transitive. The actual definition of sporadic is all the examples that you cannot fit into an infinite family nicely. So there's the alternating group A7, which is acting on the 15 points of a small projective space. There's the projective linear group PSL211 in an exceptional example on 11 points. And there's 2 other sporadic simple groups which happen to have 2 transitive representations, Higman-Sims and Conway 3. So I did this work with Max Neunhofer, and we obtained an explicit classification of all the pairs, the code words and their automorphism groups, using the computer system gap and quite a bit of theory in our investigations. A thumbnail sketch of what we found. Every group gives at least one interesting SIT code and interesting Delancre design. All up, I think there's something like 10 examples here, but we get 27 examples of codes or Delancre designs. As codes, we found all the minimum distances, and as designs, we found the parameters lambda using Leonard Deutsch's design package in the GAP computer system. Of course, we get all the usual suspects, all the Steiner systems, and if we notice, and I'm not going to give you the full list of 27, you can look it up in my paper later, but the largest has got the largest minimum distance is 50. And that occurs for an example from Conway 3. So it's acting two transitively on 276 points. And it's an example where the blocks have got size 100 in the design setting. And this design, this Delancey design, was actually found by William Hamers and colleagues back in 1993. Okay, that was exciting. That's the sporadic ones. Next, let's lump together what I'll call the projective or the rank 1 group. So these are the two transitive groups where the unique minimal normal subgroup, the SOCL, is either PSLNQ acting on the points of the projective space, or PSU3Q acting on these topic spaces, QQ plus 1, or regroups of degree QQ plus 1, or Suzuki groups degree Q squared plus 1. Now, this is work I did with Bob. What did we find? No examples from Suzuki or Ree. In the unitary groups, there's the classical unitals that Anne Delancey had found, the Hermitian unitals that she'd found with K being Q plus 1. And there's one exceptional example with Q equals 3. This is not a linear space, not one that Anne found. Her exceptions are not SIT. And this is a different exceptional example, something to do with bases. So that was fine. Then we go on to the linear groups. That's the PSLNQs, and at least 2. Well, we get lots of examples from subspaces of a fixed dimension or their complements. When n is 2 and q is a square, we get an example from taking bare sublines of the projective line. And then Bob and I had one unresolved case that I would like to tell you about. Here we've got a picture of our unresolved case. Here's a picture of the base set. So this is the points of the projective space. And so my code word is a k-element subset. And I can think, what do I know about the projective lines? They've got Q plus 1 points. They might lie inside my code word. They might lie outside my code word, or they might lie partly in and partly out. Now, because of the SIT property, the transitivity says that my automorphism group is transitive on all of these shared lines. So there's a constant intersection size. Now, geometers would say that this code word, this k-element subset of projective points, is a 0x q plus 1 subscript 1 set. That means that projective lines intersect my subset in 0 or x or q plus 1 points. Now, if I have x equals 1 or x equals q, you get subspaces or complements of subspaces. So the question was, could I have an SIT property holding for one of these subsets with x being strictly between 1 and q? Bob and I had no idea. We didn't even know this interpretation of them, but wonderful geometer Nico Durante got interested in this, and he, in this situation, he collected together a whole lot of information from various publications in the literature, and he showed that there were no more examples, no additional 0x q plus 1 points with the required symmetry conditions. So we've told you all of the examples in this case. Cool. Let's go on to the next case. So there's 2 cases left, and I'm doing okay for time. The affine case. So here, the code word, sorry, the automorphism group of the code is two transitive group of affine transformations acting on an affine space. And again, using the finite simple group classification, we know all the groups, if that's going to help. So what were Bob and I able to prove? Well, we got some examples. You have some just one one-dimensional example, a bit like the bare sublines, but here you need Q to be, the field size to be 16 in order to get the SIT property. All the other examples have dimension at least 2. We showed that if we take code words to be subspaces of a fixed dimension or complements of subspaces of a fixed dimension, you get examples. And we were able to show that if there were any more examples, then the field size Q had to be 2 or 4 or 16. Moreover, if Q is bigger than 2, we get one of these funny subsets again, because again, if we draw a picture of the point set of the affine space, think of gamma as our K element subset, and think of the affine lines. They're either contained in the code, disjoint from the code, or intersect in a fixed number of points, X. And if we get rid of subspaces and complements, then the X should lie strictly between 1 and Q. So of course, this only makes sense for Q bigger than 2. Nico again came to our rescue, and Nico Durante found for Q is 4 and 16, all other examples, and there were some really nice ones. There was one that Bob and I had noticed from the special two-transitive hyperoval in the projective plane of order 4. Nico found cylinders which intersect in crossways in this hyperoval. He found that you could take 2 parallel hyperplanes if the field was order 4, or 4 parallel hyperplanes if the field had order 16. And he could prove that there were none others. So there's a very beautiful geometrical description of all of these cases. Now, Q equals 2 is another story. Bob and I have a mistake in our paper. We assumed that all of this stuff held for Q equals 2, but Mark Iopolo, my PhD student, noticed that there was this mistake for Q equals 2. So there's yet another story here. What happens with Q equals 2? Well, the automorphism group is a two-transitive group of affine transformations. It contains the translation group in particular. Every code word determines some subgroup of translations, the subgroup of the translation group that leaves this code word setwise invariant. It might be that this subgroup is trivial. In that case, let's call the code translation free. It's got no translations fixing the code words. But it might be the case that this is non-trivial. And then Mark and I could prove in his thesis, we still haven't written the paper yet, that the code is a disjoint union of maybe just one, but in general, some number of smaller SIT codes, which we call components. Now, each one of the components turns out to be an imprimitive blow-up of an affine SIT code in a smaller Johnson graph. And this affine SIT code is translation free. So we're really interested in translation free ones. We would like a better description of these components, but the translation free ones are the interesting ones. And we have a complete classification of the translation free affine SIT codes. And the basic ones are essentially block sets of symmetric symplectic designs, if you think of them as Delancre designs. So again, I've got here unclear how many components. Whoops, let's go back to that. So we have this complete description. Sorry for getting a bit muddled. So that's the affine ones. Let's go to the last set. The last class of two transitive groups are the really interesting, really difficult symplectic groups, SP2N2 acting on sets of non-degenerate quadratic forms. There's two actions. The type could be plus type or minus type, elliptic or hyperbolic. And these quadratic forms are acting on the natural underlying space, vector space, which is not V. V is a set of quadratic forms. So now this is work by John Bamberg, Alistair Villas, and I with Mark Iopolo, our student. What have we got to say for ourselves? Well, first off, Mark has constructed some families of examples. We've got as input the dimension n and the type of the quadratic codes, that's epsilon. We have another parameter d and another epsilon prime. So in these codes, the code words are labeled by non-degenerate d-dimensional subspaces, and the associated code word are all the forms of the right type, epsilon type, which restrict to type epsilon prime on U. So we proved that they're SIT codes. There's another family which is defined rather similarly based on totally isotropic subspaces instead of non-degenerate subspaces. Moreover, we proved that these are the only SIT examples where the automorphism group of the code, now that's this full symplectic group, but when we fix a code word, we ask, how is that acting on this space? Well, if that's acting reducibly, we just get these nice families that have been constructed here. What else can we prove? Well, if there are, well, there are others, if there are other SIT codes, then this stabilizer of a code word is almost simple and absolutely irreducible. And for those of you that are familiar with Ashbacher's classification of subgroups of symplectic groups, it's a C9 subgroup. We don't know what all these are. We do know that there is at least one because Mark found one inside of SP82. He found an example of a code, hence the Delancre design, in the action on plus type forms, where the stabilizer of the code word is the symplectic group of size 10, acting here on the deleted permutation module. So there is at least one. If there are any more, they're going to be extremely interesting, and I'd love to know what they are. So that's where we are. There's lots and lots of, yeah, there's lots of challenges. Please, it would be wonderful to complete this classification of these SIT codes and Delancre designs in the symplectic case. It would be nice to know, even for the examples that we found, we don't really understand what they're really like as designs. It would be lovely to complete the proper classification description of the affine codes. And come to think of it, Delancre designs are more than being flag transitive and anti-flag transitive. Maybe it's possible to classify the two designs which are both flag transitive and anti-flag transitive. It's a strictly larger family than the Delancre designs. There's one last finale coda that I wanted to put in here. When I was doing this work with Max Neuenhofer, we were finding all these fabulous examples from the sporadic two transitive groups. And we thought, gosh, most people thinking about codes think about strings of zeros and ones. And that's thinking of codes in the binary Hamming graph. You could kind of imagine embedding our Johnson graph into the binary Hamming graph. So the Hamming graph's got vertices being strings of length Z of zeros and ones. Distinct V tuples agreeing in all but one entry are the edges. So we're going to embed our Johnson graph this way. You take your K-set gamma and you associate with it a vertex of the binary Hamming graph that's a V tuple where you put ones in the positions corresponding to the elements of gamma. So the characteristic vector for gamma. So each of these code words has got K1s. And so the code that we're getting inside of the binary Hamming graph is a constant mate code, okay? And the distance the minimum distance between code words in the embedded code is twice the minimum distance in the original code in the Johnson graph. So they've got rather nice error correcting properties. The automorphism group of the code in the Johnson graph is still acting as automorphisms of the code in the Hamming graph. It's transitive on code words. It's got 2 orbits on code neighbors, some of weight k-1 and some of weight k+1. So there's some kind of cute interplay between the codes in Hamming graphs and these Johnson graph codes. And that is certainly enough. And I am going to stop. There's plenty of papers to look at here, and there's plenty of interesting problems, and I hope someone might be interested in working on them. So thank you very much, and please everyone stay safe. Thanks.
Thank you for this very interesting talk. Are there questions?
May I ask questions?
Yes.
Can you hear me? Professor Praeger, thank you very nice. Thank you very much for your very nice talk. Of course, I'm coming from the graph theoretic side, and I can't see enough graph theory, but it's okay. Maybe they are in the proof. But I am also interested in geometric ideas. Of course, group theory also. But the first question is, because you start with graph theory ideas, that this equitable partition, the idea goes to this Zemeredi regularity lemma, that you can approximate any graph with some regular objects. So from that point of view, I can ask this, let's say, philosophical question that can you, over there you have for large n, usually. For large n, if your blocks are large, means the blocks of size n is large, can you somehow find a similar idea to decompose a code as this? You said that this partition codes maybe are not so okay, this SIT codes. So somehow related a code with a large n to decompose into these SIT codes. This is my first question.
I'm not quite sure which parameter you mean by n. But you
I mean sorry, because I'm not so good in the coding.
Do you mean the size, the order of the graph?
Yes.
The order of the graph, yes.
Yes.
So
because the Zemeredi regularity lemma is about the order of the graph.
Yes. So Delsart suggested looking for codes. He'd like to find completely regular codes, and there are some completely regular codes in nice graphs. I mean, if you look at any distance regular graph, that would be a very suitable graph for searching for codes. If you looked in distance transitive graphs, then you could even use our concept of being neighbor transitive, because this works in any graph. You might not like the symmetry conditions. There's certainly been a lot of work.
I like it.
You like it? Okay. So there's been quite a lot of work on neighbor transitive codes in Hamming graphs. Many papers published on that. There's just these few papers published on the case in Johnson graphs. And as far as I know, there's been no studies of these concepts in other families of graphs. That would be a very natural and interesting thing to look at. The particular specialty about the Johnson graphs is the link with designs, as well as the interpretation of codes in the graphs. But you can have this neighbor transitivity, or you can restrict the oops, where have I got it? Got to go backwards. The definition of equitable to just going out in a certain distance instead of the whole way out, because people have really looked very hard for completely regular codes, and perhaps the ones they found are beautiful, but maybe maybe it would be possible to get a richer family if you did not ask for this regularity property to go too far away, a distance from the code words.
And my second question is that you mentioned this the joint work over this projective plane and Q, PJN-1Q, am I right? I can't see the page number to say
okay,
which page
go.
it is. So, so my question is, I see that your work is much more geometric ideas than graph theoretical ideas. Sorry, it's my sense.
Yes, that's true. This particular project is really much more
because of the
theory.
geometry. Because of the geometry, I suggest that what if we, instead of having this this Johnson graph and the code, why we go directly to geometrical stuff like Grassmannian codes? So instead of Johnson, we go to the Grassmannian and these new Grassmannian codes, and then we consider that.
I think that's an excellent idea.
Yeah, this is exactly, you go through the Q. In combinatorics, we say that this Grassmannian is the Q analog or quantum analog of this Johnson. Yeah, so it is very natural to consider that instead of considering this process. Sorry, I'm not expert. I just
it's a very nice suggestion to try out some of these ideas and concepts in the Grassmannian graphs. Definitely, I imagine the story would be very different, and it would be very interesting to know what it was.
So I'm really interested in that, and if you, so we can write about it later by email or something. Thank you very much. Thank you very much for your very nice talk.
You're welcome.
More questions? Okay, so actually I also wanted to ask a question. You had this in the linear group case, this you called it unresolved case. And I mean, this sounds interesting, this 0x(q+1) set. So why exactly do you call it unresolved? Because there's
it was unresolved by Bob and me. And Bob died in 2009. And before I'd managed to finish off this paper, I gave a talk about the case, explaining the properties of these sets. And Nico Durante was in the audience at the time, and he actually resolved all of these cases. But these are sets which are very much studied by geometers. I didn't know all the results, but he did, and it was fantastic that he could work out that there was enough in the literature with the appropriate symmetry results, so that he could see that there simply were no possibilities in the projective case. But on the other hand, in the affine case, he found these amazingly beautiful geometrical configurations which gave examples, which was kind of similar. You see, this number 1 refers to a condition on one-dimensional projective lines. And they look at these subsets with perhaps a different number here, maybe S-dimensional subspaces intersecting the set in certain sizes which are allowed. And sometimes they look at, well, I don't know who they are. I think it's a very natural question to be looking at in finite geometry.
Okay, thank you. And do you know, is there a nice geometric description of these sets?
Yes, in Nico's paper, he talks about them. so I would refer you to his paper, and I've got the paper at the end of my talk here, but it's probably best to look in the BCC proceedings, because in that list of references, you can track down Nico's paper there.
Okay, great. Thank you. So let's see if there are more questions.
If there is no question, I want to ask one more.
Okay.
Can I ask?
Yeah, please go ahead.
Yeah, very quickly, Professor Praeger, my last question is that you mentioned this embedding of graph. So it is one of my favorite area. And when we talk about the embedding of this Johnson graph in this Hamming graph, we usually interested to have a isometric embedding.
Yeah, so this is not,
of course, it is not isometric, but near to isometric, two-wise, something like that.
It's not a graph monomorphism. So it's a bijection.
Yes.
But vertices at distance 1 in the Johnson graph get mapped to distance 2 in the
my question is that usually when we, in graph theoretical sense, when we embed something, we usually go to this spectral techniques. So maybe it is weird here, but usually this embedding, when the people looking at the embedding, they're looking at this eigenvalue and eigenvectors or something like that. Have you?
I don't know. I mean, this is a very small part of the Hamming graph.
Sorry, for my question.
Yes, so I don't know what to expect. I would defer to my colleagues who know more about eigenvalues than I do. I'm afraid I can't really comment on it. But it may be that this is a very interesting subset from that point of view.
Thank you very much. Thank you for.
Yeah, let's thank you again for this great talk. And then the next, so the conference continues in half an hour.